Hi guys, welcome to the worksheet walkthrough for question 2, which is on the Chinese remainder theorem. So part 1 has us find the smallest positive integer which fulfills the following conditions. So here we have a system of modular congruences, where the first one states that x is 3 mod 7, it's also 4 mod 5, and finally it satisfies 1 mod 2. So this is a system of 3 modular congruences. And we have a system, and also we can see that the mods themselves, 7, 5, and 2, these are co-prime, so they share no common factors. And because we have this condition, we are now allowed to use the Chinese remainder theorem. So what CRT states is that there is a unique x mod the product of these mods. So 7 times 5 times 2 is equal to 70. So there is a unique x mod 70, which satisfies all 3 modular congruences at the same time. And this is also a constructive theorem, so it gives us a procedure to finding this exact x. So we can apply the formula in order to get this number. So the first term is going to be 3 times big N over little n1 times big N divided by little n1 inverse mod n1, and so on for the other 2 terms. And as we see, we can do some simplification of the mods. So first of all, we turn 70 over 7 into 10, and then 70 over 7 inverse into 10 inverse. We did this with the second term and a third term as well. And then on this line, we actually compute the inverse. So we notice that 10 inverse mod 7 is the same number as 3 inverse mod 7, since they belong to the same sets of modular numbers. So 3 inverse mod 7, well, that's just 5, because 3 times 5 is equal to 15, and then 15 mod 7 is congruent to 1. So we repeat the same process for the second term. We find that 14 inverse mod 5 is 4, and the third term, 35 inverse mod 2, is 1. And if we do the multiplication, we're going to get these large numbers, and all of this is being modded by 70, because that's what the Chinese remainder theorem guarantees. This number is going to be between 0 and 69. And lastly, to simplify further, we can turn this 150 into 10, and in this 224, we subtract 210 in order to get 14, and 35 just stays at 35. So the final answer that we get is 59 mod 70. And you can check that 59 mod 70 does indeed satisfy these 3 modular congruences. For example, 59 is congruent to 3 mod 7. Because what is this? Because we have 7 times 8 plus 3 is equal to 59. And you can check the same for the second one and the third one. So yeah, CRT generated a solution that was able to work for us. But how did it actually come up with this solution? The Chinese remainder theorem on 3 modular congruences works by summing up 3 very special terms with special properties. The first term that we see is 3 times 10 times 10 inverse mod 7. And if we focus on in this part in the bracket right here, this number here is 0 mod 10 and 1 mod 7. And we can prove this by just directly taking the mod of this. So we have 10 times 10 inverse mod 7 and let's say we try to mod it by 10. The number inside here is just an integer. So this number is of the form 10 times k for some integer k. So we end up with this is congruent to 0 mod 10. What's more tricky is recognizing that when we mod this by 7, we end up getting 1. So when we mod this by 7, we notice that we multiplied it beforehand by 10 inverse mod 7. So trivially, this just gives us 1 mod 7. And we notice with the other two terms, we get a number that is 0 mod 14 and 1 mod 5. And finally, we get a number that is 0 mod 35 and 1 mod 2. So a very good way to view Chinese remainder theorem is from a linear algebra standpoint. In linear algebra, we have the concept of basis vectors. And in this case, the kind of basis vectors are these three individual numbers. And this first number controls to what degree a number is mod 7. This number controls to what degree a number is mod 5. And this third number controls to what degree this number is mod 2. And then for each of these three terms, we also need to force it to be 0 mod everything else, because we want this number to not affect any of the other terms. So when we sum this up and when we scale it by the coefficients, this entire first term gives us a number that is still 0 mod 10, but now it's 3 mod 7. The second term in its entirety now gives us a number that's 4 mod 5. And a third term gives us a number that is, well, we scaled it by 1 here, so it's 1 mod 2. And if we add these three numbers together, we end up getting a number x that indeed does satisfy all three of the modular congruences above. So that's sort of just an intuitive view on why Chinese remainder theorem works. Now we're going to talk about number 2, which is under the premise of a supermarket has a lot of eggs, but the manager is not sure exactly how many he has. So let's first let x denote the number of eggs, which is currently unknown. And the manager notices that when he splits the eggs into groups of 5, there are exactly 3 left. So in mathematical language, we have a remainder of 3 eggs when we mod by 5. And similarly, when we split the eggs into groups of 11, we have a remainder of 6 eggs. And the question is, what is the minimum number of eggs at the supermarket? So immediately, we can set up a system of modular congruences. In this case, we have the two modular congruences, x is 3 mod 5 and x is 6 mod 11. And because 5 and 11 are coprime, we can then use the Chinese remainder theorem to get the answer 28 mod 55. Now notice that 28 mod 55 is not the only solution. We can also add any factor 55 to get a valid solution. So for example, 55 plus 28, that gives us 83. So 83 is also 3 mod 5 and 6 mod 11. However, it remains a fact that the smallest possible x is just the smallest number that's returned by CRT. And this number is always going to be between 0 and 54 in this case. So the correct answer is 28.